So our topic is on Newton's first law of motion, and the main idea of Newton's first law is that an object at rest, not moving, stays at rest, and objects in motion stay in motion unless acted upon by an outside force. So let's talk about what a force is and how we define it. So this would be a good point, if you haven't already done so, to take out your notebook and then take some notes on what we're watching here. This is also posted in the week 4, day 1 outline, the link to this document if you want to go back through it. And in a second you're going to be watching a video from it. But now please pause and get out your notebook if you haven't already. So a force is a push or a pull, and it's also a transfer of energy. So what we're saying is that push or pull transfers energy from one object to the next. For that reason, there's always two objects interacting. And we're going to create what we call an interaction diagram that will show all forces and the pairs, the objects involved in the interaction. So here's Newton's first law. So objects at rest would be not moving, and that unless they're acted upon by some outside force, that they'll stay that way. And that objects in motion will stay in constant motion unless acted upon by an outside force. This is also the idea of inertia. Now keep in mind, motion and forces are different things. Motion itself is not a force. It is the result of a force, an unbalanced force, or depending on what you're comparing it to. So motion is not a force in and of itself, but acceleration of force. So this should all be big in your notes. You should have the date, the 16th, topic 1, cycle 2, learn, and this is a key idea for our whole topic. So what I'd like you to do now is to pause the video and go into the outline for today on Schoology. Remember, we're in week 4, day 1, and there's a video called Huge Jenga Tower. So what I want you to do is watch that video with your group and talk about how that video is an example of Newton's first law of motion, which is right here. I also want you to identify how it shows forces, push or pull, transfer of energy. So how does this stay true with Newton's first law of motion? So please pause now, go into our Schoology outline, and click on that link to watch the YouTube video for a Huge Jenga Tower. It's also in our lesson today, up here linked at the top if you're having trouble finding it. So, if you haven't yet watched the video with Jenga, then watch it with your group and pause this video. Once you're done, you should go into these examples with your group. So here we have two men of equal strength playing tug-of-war. Who will win? Remember, this man's pulling this way, the second man's pulling to the right. And then if they're each pulling with 10 newtons of force, a newton is the unit that we use to describe force. So what's the total force applied to the object or to the rope, or the net force? So keep in mind that force, like velocity, is a vector. So we write that little half arrow on top of it to show that direction matters. A vector means direction and magnitude. Another word for magnitude is amount. It matters, just like velocity is how fast you're going, your speed, and your direction. Force is how hard you're pushing or pulling, and in the direction that you're pushing or pulling. So if they're each pulling with 10 newtons of force, what will be the total force applied? Explain this using numbers. Pause now and explain your answer. These should be going in your notes. Okay, so we should see that if they're both pulling with the same strength in opposite directions, that the force will balance out. If this gentleman's pulling with 10 newtons to the left, we'll consider that positive. When we add that to this guy's force to the right, we'll consider that negative. 10 plus negative 10 is 0. That means the net force on the rope is 0 newtons. That's what we call balanced forces. When forces are balanced, when the net force on an object is 0, that's when Newton's first law applies. That objects at rest will tend to stay at rest. So if this rope was not moving to start, it'd be staying at rest because the net force is 0 on it. If it was already moving, it would move at a constant pace, constant motion, because the net force on it's zero. And another way, again, that we say that is forces are balanced. Okay, look at D and E here. So now we have two men on either side. Like, so every one of the guys has a double. Does this change the result? And then explain this using numbers. Pause now and do that with your partner. You should see that now it's just 20 newtons this direction. We'll consider this positive because these guys are pulling the other direction. We'll consider that negative 20 newtons. When you add those up, we get a net force of 0. And again, Newton's first law applies. Objects that are at rest will stay at rest. There's no net force on the rope, so it'll stay where it is. Now let's look at another example here. Now we have 3 gentlemen pulling with 10 newtons to the left and 2 pulling with 10 newtons each to the right. Well, now forces are not balanced because we have 10 plus 10 plus 10, or 30 newtons left, and negative 10 plus negative 10 are negative 20 newtons, and that 20 newtons is to the right. So our net force would be 30 plus negative 20, which is 10 newtons. So these are unbalanced forces that'll result in acceleration. Okay, go through F, G, H, and I. Pause now and finish. I'd like you to now draw an interaction diagram for this last drawing. You can just draw 3 stick figures on the left with a rope and 2 on the right. And then you just want to show with an interaction diagram, it's like an outline for everything included in this system. So all the forces are joined with an arc in the letter of the force. We list contact forces in the upper left and non-contact forces in the upper right. Examples of contact forces are the normal force, the force that opposes gravity or when you're pushing on something perpendicular to it. Another one is friction. There's friction on their hands and the rope. There's friction of their shoes on the floor. And non-contact forces include gravity, magnetism, and electrostatics. Right now we're really only concerned with gravity. So keep in mind that gravity is a non-contact force. That means 2 objects don't have to be in contact for that force to be acting on the 2 of them. So I'd like you to pause now. So here's some advice on making an interaction diagram. So let's see what an interaction diagram would look for this system. When we say system, we're just talking about certain objects that we're including in our description, certain objects that we're interested in for our research or question of interest. So here I would circle these. I'm interested in the wagon and the horse. I would always draw Earth below if they're on Earth, and then I would go from there. So here we have our interaction diagram. Every force pair is connected with an arc and then the letter describing the type of force. So every arc represents a force. There's friction between the feet of the horse and the ground, and the wheels of the wagon and the ground. There's a normal force. We know there's normal force because the boxes and everything isn't accelerating through the ground or up in the air. So it's constant motion or balance forces. Okay, so now take this picture of a horse, a wagon, and the earth and turn it into an interaction diagram. Start by drawing the objects in earth and then connect any 2 objects that have a force interaction between them. Pause and do that now. What we can do once we have that done is circle any object and then draw a force diagram for it. So a force diagram shows us all forces acting on any object in a system. A system being any group of objects that we're interested in looking into. So we draw a circle around the wagon, and any of the little force pairs that go through it we know is a force acting on the wagon. We would then list contact and non-contact forces. Non-contact force would be gravity here. The 2 objects don't have to touch for gravity to be there. And contact would be like tension, or a normal force is a force perpendicular to an object applied to it, and friction. Okay, so please go through number 1 and 2 here with your group and complete your interaction diagram and a force diagram, and then calculate the net force acting on each and explain how it's an example of first law.